Welcome to your video lesson on how magnetic forces influence a moving charge in a magnetic field. By the end of this lesson, hopefully you'll be able to explain both quantitatively and qualitatively how a uniform magnetic field affects a moving electric charge using the relationships between charge, motion, field direction, and strength for when a charge is moving perpendicular in a magnetic field. So what does that mean? That means that by the end of class, you will hopefully be able to look at a charge that is going perpendicular through a magnetic field and determine the direction of the force, and eventually using some calculations to figure out the magnitude of the force depending on the speed of the electron, the strength of the magnetic field, and the charge of the electron. So you're going to be learning in this video another hand rule to help us with these calculations, to figure out qualitatively these relationships, and then you're also going to look at certain calculation questions to figure out the exact forces and magnitudes of the magnetic field lines, the velocity, and so on. So let's take a look at this picture here. Basically, if I close this circuit, I will get a current that goes around this can, kind of like a solenoid that we learned in the last video. Now what ends up happening is when the current is going this way, it creates a force that will actually end up crushing the can. So remember, we learned that current moving creates a magnetic field. And in this case, we're going to be having a current interacting with a magnetic field, which then creates a force. And we're going to learn how that works here today. When Oersted discovered that moving electric charges create a magnetic field, it was only natural for him to investigate what happens when the moving electrons are placed inside the magnetic field. These investigations led themselves to many practical applications and interesting problems that we are going to study. So what did Oersted notice about electrons in a magnetic field? Well, there was an interesting experiment done which showed that when electrons or charged particles were placed in a magnetic field, they were accelerated, but yet their speeds remained the same. So what was happening here? I have a video here to help us understand what's happening. So here I have a cathode ray tube. What that is a vacuum with pretty much an electron beam shooting through the vacuum. So we have electrons, which are negatively charged particles, being shot through, making this beam, which is called a cathode ray. Now what's going to end up happening here is a magnet is going to be brought towards this electron beam, or the cathode ray. And we're going to see an interesting interaction that happens. So remember, these are negative charged particles flying through this vacuum. So here we go. Magnet was brought. First, it deflected the beam upwards. Now it's deflecting the beam downwards. As I move the magnet, the beam starts deflecting earlier. So, if we look at that magnet there, when the magnet was brought close, the magnetic fields were causing the beam to deflect. So that must mean if the beams deflect, these electrons must be undergoing a force that causes them to move. And if there's a force, that must mean there is an acceleration. And we know this because the cathode ray is deflecting away. The ray is bending, changing directions. So that is how we end up having an acceleration, but yet the speed remains the same. Because remember, speed does not have a direction. How do we figure out the direction of this force? How do we figure out the power of this force? Well, we're going to learn about that in this lesson. So before we get into how that works, I have a Venn diagram here for you to copy down, which compares how electrons or charged particles move in electric fields compared to magnetic fields. Now, both of these, electric and magnetic fields, cause the charged particle to accelerate. But the electric fields, they change the magnitude of the velocity. So we'll either speed it up or slow it down. An example is changing from 80 kilometers an hour to 100 kilometers an hour. While magnetic fields, the particles tend to be on cruise control. They do not change speed. These particles move in circles, so they end up being deflected, and therefore can cause a change of direction only. Alright, now we're going to learn our third hand rule. This hand rule will follow the same rules as the hand rule before. So right hand is going to be used for conventional current, which means positive charge, the movement of positive charges. Our left hand is going to be used for electron current, or the movement of negative charges. If I look at this right hand here, we have three variables interacting with each other, which is different from our previous two hand rules, which only dealt with two variables. In this case here, we use our fingers to always line up with our magnetic field. So we're going from north to south. So the fingers will go from the north to the south pole. My thumb is always going to be the velocity of the charged particle. Once again, I use my right hand for positive particles, and I'm going to use my left hand for negative particles. And the thumb indicates the direction. And then now we have a third factor here, which is going to be my force. And my force is going to be coming out perpendicular from both the magnetic field and the velocity, and directed out straight from the palm of your hand. So conventional current is, once again, right hand. Electron flow is left hand. We know that we place the fingers from north to south to represent the magnetic field. We also know that we have to use our thumb, and that is going to be the direction of the charge flow. Then, lastly, we know the palm is going to show us the direction of the magnetic force. So the direction of which it will deflect the charge. Now, it is important to note that the force is always perpendicular to both the magnetic field and the direction of the charge flow. This is why the speeds stay the same and the force is a perpendicular direction of flow. Therefore, no work. One thing to note is that we always need the perpendicular speed of the charged particle to the magnetic field. Let's take a look at an example here to see how we use this third hand rule. Now, I have an electron moving through a magnetic field, and we want to see how it is deflected. So the fact we have a movement of a charge, and we have a magnetic field, and we want to see the deflection, that's three different things, we know we're going to have to use our third hand rule. And it's going to be a negative charge, so that means we're going to be using our left hand rule. Now I want to know which way it is going to deflect. So basically, I have to first put my fingers going from north to south. And then I'm going to put my thumb, my left thumb, pointing in the direction of the electron flow. And then my palm will tell me which way the electron will be deflected. So if I look at it here, I have my magnetic field, fingers follow my magnetic field from north to south, thumb follows my electron flow, and then my force is going to go into the page here, or down. So my force will be deflected down. Now I have three here for you to try. In the first one, we have a negative charge, so that should tell us which hand we're going to use. We also have a force, so which part of the hand is the force? Which part of the hand is the moving charge? Let's look at the second one. The second one here, we have a negative charge as well. So which hand should we use? I have a magnetic field going in this direction. So which part of our hand do we use to line up with the magnetic field? My force is going down. So which part of my hand must I use to line up with the force? And then my last one, I have a positive charge motion with the magnetic field going this way to the right, and we have a force going down. So we have to line up the sections of our hand to each of these vectors. And remember, the charge will tell you which hand to use. So I want you to pause the video and try and solve these questions. So let's see how you did. In my first example, it's an electron moving, so that must mean I'm using my left hand. I am going to line up my left thumb with the electron. Now my force is going up, so that means my palm must face upward. Kind of like this. So that means my magnetic field follows my fingers, which are going to be coming out of the page. And if you remember, we're going to put a little circle with a dot. So it's like an arrowhead coming to you because it's coming towards you. Now for B, here I have a negative charge again, so I'm going to use my left hand. My force is going down, so I'm going to put my palm down. Then I have to line my fingers, my magnetic field, going to the left. So I push my magnetic field to the left, and I find my thumb is going to be going into the page. So in this case, we're going to have something like that. So remember, it looks like an arrow going away from you. It's moving away into the page, so it's like seeing the back end of an arrow moving away from you. Then, for my third one, we have now a positive charge. So in this case here, I have to use my right hand. First, I'm going to have my palm, it's going down. My fingers are going to be going to the right, and I'm looking, my thumb is into the page. So this one here is into the page as well. It's going to be my electron flow. Now we're going to learn how to quantitatively calculate the magnetic force. By studying different types of deflections, scientists can also explain the complex deflections of charged particles entering a magnetic field at an angle, such as the particles that cause the auroras. The magnitude of the deflection force depends on all of the following. It depends on the magnitude of the moving charge, the magnitude of the perpendicular velocity component, and the magnitude of the external magnetic field. So the magnitude of the deflecting force can be calculated using this equation here. Now you might be wondering, what happens if the charge enters the magnetic field but is not perpendicular to it? How do I do calculations then, since it says the velocity needs to be perpendicular? Well, in that case, we're going to break it down, the velocity of the charge, into two components. We're going to break it down so we can find the perpendicular speed of it to the magnetic field. And to do that, we're going to use this formula here, where my perpendicular velocity is going to be equal to the velocity multiplied by sine the angle of which it enters the field at. If you remember from math class, you learned that sine 90 is going to be equal to 1. So any velocity that enters the field at 90 degrees is just going to be multiplied by 1. So it's just going to be equal to the perpendicular velocity. But if it doesn't, we just go sine that angle, and that will give me the perpendicular velocity. Let's take a look at my first quantitative example here. I have an electron with a charge of 1.6 times 10 to the negative 19 coulombs traveling at a speed of 3.2 times 10 to the 5 meters per second perpendicular to a magnetic field of 2.2 times 10 to the negative 1 teslas. Determine the magnetic force acting on the electron. So now I'm going to use my formula for magnetic field, which is equal to my charge of the electron multiplied by my perpendicular velocity multiplied by my magnetic field strength. That's going to give me 1.6 times 10 to the negative 19 coulombs multiplied by 3.2 times 10 to the 5 meters per second multiplied by 2.2 times 10 to the negative 1 teslas, which will end up giving me a total of 1.13 times 10 to the negative 14 newtons. Now I have to figure out here what direction that force is. Since it's a negative charged particle, I know I'm going to use my left hand. I am going to line up my thumb with the direction of the particle into the page. Then I'm going to line up my fingers from north to south. And that will tell me that my force is going to be coming out of my palm upwards. So I'm going to end up getting 1.13 times 10 to the negative 14 newtons upward. So let's take a look at our last question here. We have a carbon ion with a mass of 2.1 times 10 to the negative 26 kilograms and a positive charge of a magnitude of 1.6 times 10 to the negative 19 coulombs, which enters a region of external magnetic field of 6.32 times 10 to the negative 5 teslas. Find the perpendicular speed at which the magnetic deflecting force will balance the gravitational force such that the carbon ion will travel in a straight line. Now, looking how the question states that the magnetic deflecting force and the gravitational force will balance, we could assume that that means that they will be equal. Seeing as the gravitational force is going to go down, I'm going to assume that magnetic deflecting force is up. And we could test it using our right hand rule since it's a positive charge particle. I'm going to use my right hand for my thumb to say the velocity, so it's going into the page. I'm going to use my fingers to go north to south, and then I'm going to find out that indeed the force is going up, which will be the opposite of the gravitational force. So I'm going to start off here by looking at it that my magnetic deflecting force will equal to my gravitational force. We know my magnetic deflecting force is going to be the charge multiplied by the perpendicular velocity multiplied by the magnetic field. I know my force of gravity is equal to my mass times my gravity. Now I want to isolate for my perpendicular velocity. So that's going to give me the perpendicular velocity is equal to mass times gravity divided by magnetic field times the charge, which will end up giving me 2.01 times 10 to the negative 26 multiplied by 9.81 divided by 6.32 times 10 to the negative 5 multiplied by 1.6 times 10 to the negative 19 coulombs, which will give me a total of a velocity of 1.95 times 10 to the negative 2 meters per second into the page. So at the end of this video, I want you to prepare yourselves for an activity that we will do tomorrow in class. We're going to do this concept check by making a poster. Tomorrow, I'm going to break you up into groups of 3 or 4. In these groups, you're going to have 7 minutes to brainstorm ideas and put as much down on a piece of paper about magnetic, gravitational, and electric force. Include as many examples as you can. After that 7 minutes, you are going to get a chance to look around at what other groups have done. And then you're going to get another 5 to 10 minutes to finalize your poster and hand it in. So you have something now to think about and contemplate before tomorrow's class so you can make this poster with your group.